Okay, well, let's get started. Welcome to Lecture 16 of 5828, Foundations of Software Engineering. Today is the lecture that I've reserved for doing our midterm review. So I don't have any prepared slides for this lecture. What I would do to kick things off is just summarize what we've covered so far. And then highlight some of the key important things that we've looked at, and then I'll open it up for questions, and we'll go from there. So we started the course with that lecture one was mainly a course overview, my goals for it and the like, but towards the end of that lecture slide, we started to get into a little bit of content and discussed some definitions of software engineering. Talked about, what does engineering mean anyway, and how does it then intersect with our discipline of software engineering and our discipline of computer science. We talked about the relationship between computer science and software engineering, and that appeared on the first homework, I believe, where we talked about some of those analogies of the what's difference between a chemist and a chemical engineer, and we asked about computer scientist versus software engineer. And basically the focus is on, for engineering, the focus is on practicality and scalability, repeatability. We try to take techniques that are developed in isolation, and we ask, how can we use these techniques in a context where we're trying to build very large systems? And we talked a little bit about, if I bring up the slides here, this definition of, let's see here, nope, not new, open. So this is these definition-related slides, and we have this one that talked about, this one. So this one kind of really pulls everything together about what software engineering is. The engineering aspect is that we need systematic, disciplined, and quantifiable approaches. So systematic means that we have kind of a comprehensive view of the whole process of software engineering. And we have processes that we've created that will help us start a project, go through the middle, and come out at the end with some sort of working system. A disciplined approach means that we are committed to following these processes, learning the best tools and techniques, bringing them together. And that quantifiable means that we want to be able to make sure that we're measuring our progress in some way, and measuring how we do so that we can learn from those results and apply that in our knowledge of how to then run subsequent development projects. And then it also is the discipline that takes the principles of computer science and design, so that could even be product design, industrial design, ergonomic design, etc. So it's referring to design in general. Engineering, management, mathematics, psychology, sociology, and other disciplines. And the other disciplines come in as you intersect with application domains where some other discipline might suddenly become relevant for you to understand the domain and its requirements and the needs of its users and the like. Two, and we use both of those to help create and develop, operate, and maintain software systems, which are solutions to software problems that are cost-effective, reliably correct, and high quality. So that really kind of brings everything together in one definition. And so I might ask you in the midterm questions that touch upon this definition, or what software engineering is in general, how it relates to computer science, the types of approaches we're supposed to be developing, and the like. And towards the end of this lecture, I also talked a little bit about these issues of scale and issues of communication, trying to just bring in distinctions between just programming and the discipline of software engineering. Programming just becomes one of many things that we have to worry about and be able to do. I talked about the different types of software development and jobs. And then more importantly, these last couple of slides that had questions that also appeared on the homeworks about some of the core principles and this notion of specification. What is it that we're working against? How do we know if we're making progress? Or How do we know if we're building the right thing? Well, the default answer to that is, do we have a specification that we're working against? And so then in general, we'll ask, well, what is it that makes good specifications? And if I'm looking at a specification, will I recognize the specification when I see it? And if you start to pay attention, lots of things that seemingly play some other role are in fact playing the role of a specification. So for instance, if you've ever used the Ruby on Rails system, they have preference files that identify what your database connections are, what your user names should be, how to do migrations of the database. All those things are in specifications that the Ruby on Rails suite of tools operate upon. We also talked about how we're always doing the work of translation from one specification to another, or from one layer of abstraction to another, or in a software system, transforming our inputs into outputs. And then the important role of iteration, the role of decomposing problems from big problems into small problems, and then iterating on those problems until we've got them solved. And then I added just a few things, two more things, which was, one was this notion that a key thing that we do is work with abstractions. And so whenever we say API, or what does this tool provide, or what is the services that this web service provides, we're talking about an abstraction. And either we're building those things and therefore developing the abstraction, or we're using those abstractions developed by others. And the abstractions here are concepts that help us break a problem down into something that's understandable. And if I was using this abstraction, I would want it to be able to help me solve a problem. So if you look at a library in an application development environment context, like if you're building Cocoa apps for OS X, there's all sorts of frameworks that they provide. Things that do audio and video, things that do authentication, a framework for doing undo and redo of commands. All of those things, all those frameworks are abstractions that you then have to work with, understand how to initialize, how to pass data to, how to use, in order to then have your application do something as a result. So it is abstractions everywhere. And so one of the things that we have to do as software engineers is become good at using abstractions, understanding them, creating them, designing them. And then the last thing was the final five of these five major things that I discussed. The last one was this importance of conversation. And in our lecture 14, we're going to talk about that, or we talked about that in the context of user stories and how those serve as requirements. But the important thing about those user stories was the fact that they are basically a representation of conversations we need to have with our customer to be able to understand the requirements for a software system. And so that's just an example of how conversation becomes important in software engineering. But basically, we have to be committed to asking questions of our users, asking questions of our fellow developers, asking questions of the source code by interacting with it, searching through it, indexing it. However, we're always having conversations of some sort to reveal information, to go from a state where we have less information to a state where we have more information. And so we can't emphasize enough. And I highlighted how a lot of the tools that we work with, things like GitHub and issue trackers, things like FogBugs, which is an issue tracking system, all of those things are designed to facilitate coordination, collaboration, and communication, conversation. All right, so don't forget about little lecture 1 just because it's called course overview. There was actually some content hiding in those slides. We then moved on to talk about the theoretical foundations. Oh yeah, question.
Sorry, so you said 5, so the core principles are the 5: specification, translation, iteration, abstraction, conversation?
Yes, those are the 5, yes. So then we moved on to talking about No Silver Bullet. I like to do this reference to Fred Brooks's work because it's one of the papers that are out there that just makes the case for why software engineering is so hard, why it's so complex. And he was writing this from a standpoint of real experience, having done traditional engineering, a hardware-based project, and then encountering all sorts of difficulties when he did his first management of a software engineering project. And so No Silver Bullet came out about 2 decades after all the work that he did on the IBM 360, but it was and in between he had spent a lot of time doing computer graphics and building systems in that area of research, but it really was a kind of a considered view from a distance of what software engineering was all about for him. And so if I bring that up, some of the key things in this lecture that I could test on will be these definitions of what a silver bullet is. Right, he has his overview where he's making the assertion that there is no silver bullet. And from this assertion, you can, from those qualities that I highlighted there, you can identify what his definition of a silver bullet was. A single technique or technology that by itself can deliver an order of magnitude improvement to some aspect of software development. Even if we could have something that comes in and makes us 10 times faster on testing, we would consider that a silver bullet. Right? Even though nothing else changed, our requirements are still hard to do, design's still hard to do. If something came in and made testing 10 times faster, he'd consider that a silver bullet. If something came in and made design 10 times faster, that would be a silver bullet. It's not like the silver bullet has to come in and solve everything. It's just got to make us, he doesn't even say that, he's just saying some aspect of software development, 10 times faster. And then he says there's just no such thing. No such thing except for hard work. And the reason why he did this again was he constructed this argument. And I like to have the students kind of have this clear in their head of when we're working on software development, we have these 2 types of difficulties, essential difficulties and accidental difficulties. And his argument boils down to the fact that when we build software tools or come up with new techniques, we're almost always doing that in response to perceived problems of an existing method or tool. And so those problems that are related to tools or our techniques are the accidental difficulties. We chose this technique to get some benefit A, but it also provided some problem P. And so when we create a new tool, we're trying to get rid of problem P and hopefully improving on benefit A. But unfortunately, then the new tool will bring in new difficulties related to it that may not become clear. They might not be immediately obvious, but they start to show up after we've used them for a while. And so the basis of his attack, or the basis of his argument, is to say, well, accidental difficulties are the ones that we traditionally solve when we're creating new tools, new techniques. And so if we're ever going to see a new technique come in and give us a silver bullet improvement, a 10-time improvement, then when we're facing our difficulties, the accidental difficulties have to account for 90% of the difficulties that we're encountering, and then that single technique needs to come in and make that all go away. And if that happened, we would see a 10 times improvement overall in our software development. But the argument goes on to say that the problem is that no tool is going to be able to reduce anything to 0, and the other aspect is that the accidental difficulties are not anywhere close to being 90% of the problems that we deal with, and that's because of the essential difficulties. And the essential difficulties, he's categorized these things as basically complexity and conformity, changeability and invisibility. They're really all aspects of complexity, right? So it's just complexity in general, but there are subtypes of complexity that we deal with, and so he broke out several areas. And if you're just looking for pithy descriptions of these essential difficulties, complexity would be the software artifacts that we create are complex, the problem domains that we attack are complex. If we model the complex problem domain, there's going to be complexity in what we model. And that complexity comes from the real world, and so is not something that's going to be going away. The real world's always going to be complex. Conformity, however, is a special type of complexity, which is the ones, it's like our own goal against ourselves. Like, take the soccer ball and go the wrong direction and score a goal for the other team. Because conformity is all about arbitrary complexity that we've imposed because some humans made some weird decision or some legacy legacy part of our environment, can't be worked around, and so we have to conform to it, and arbitrary complexity is imposed upon us. And it's really insidious because it's the type of complexity that can't be planned for. It's arbitrary in nature, it's capricious, it's random. If you were to start a project and say, hey, let's plan on what should we do if the person who's our customer decides to completely change everything on us. You just can't make any progress if that's what you decide to do up front. You have to say, well, this is what they're saying today, this is what we got to work on. If they change their mind, we'll have to deal with it, but we can't, also simultaneously be developing some other system because there's an infinite number of options as to what they might change to. And so you just have to work hard to be ready for this kind of complexity to be imposed upon you, and then just deal with it once it surfaces. Changeability is that type of complexity in which in a larger ecosystem of a much bigger project where you have some work being done on process, some work being done on hardware, and some work being done on software, oftentimes the business process evolves slowly and so is not going to be subjected to change. In fact, you might be building the hardware and the software to support some long-standing business process. The hardware itself is very expensive, has gone through lots of iterations. It's going to be, it's going to require big, large-scale manufacturing and the like. Once they've got that set, it's very expensive to change, and everyone knows that. And so what's left? Software in these systems. And so the pressure to change software, since we know we can open up a file, do a few edits and save, and we've got to change, the pressure to then change software is really intense. And so in a big project where no one might even think to question whether the hardware should change or the process should change, people just expect the software to change. And that really is kind of unfair to the software engineers. And it's also that we also talked a little bit about how users or non-technical users, non-developers even, or more appropriately, have a hard time distinguishing among types of change. May not know enough about programming languages or software frameworks to understand when they're making a request that's really hard to do versus one that's really easy to do. And so we have all of that kind of wrapped up in that changeability notion. And then finally, invisibility refers to how hard it is to just get a handle on all aspects of a software system. You have its requirements view, its design view, its how do we implement it, how are we testing it, what's its structure, both conceptually and both in terms of how it's deployed. If it's a big system, how many different machines does it get deployed on? And for each class of those machines, server, client, middleware, persistence layer, what components get deployed upon it, and how do we bring them up, how do we configure them, how do we update them, how do we manage them. And all of these things, if you want to get a handle on it, requires a new diagram. And it's really hard to merge diagrams to show the deployment view and the requirements view, or the object-oriented view of our class hierarchy with the behavioral view of what the software is actually going to do. And so every time we try to visualize it, we have to create a new diagram and then just say, this diagram and this diagram are related to the same subsystem, I just can't show them on the same slide because the notations mean different things. And so you're constantly struggling to get these big picture views or these insights into what your software system is doing. And you have to learn as a software engineer to recognize that when I'm being shown something, I'm giving a talk later today where I've got a bunch of architecture diagrams. So, in my own work, I've done architecture diagrams as simple as this, or a kind of a runtime view of a system with a server and clients, to an in-depth view of what a server is doing, which threads are running inside of the server, down to this architecture diagram that shows how we're using Cassandra and Postgres and Hadoop and Solr and Redis to do something called Epic Analyze and Epic Collect. Each one of these diagrams conveys different information, right? And if you look at this, this really tells you nothing about how Epic Analyze is implemented internally. Like this diagram doesn't reveal that it's a Ruby on Rails app, or what controllers it has, what endpoints it responds to, how it interacts with Solr, how does it interact with Redis, when does it call each. None of that is contained in this diagram. It's just saying, overall, our ecosystem consists of all of these components. And someone has to go out and make sure Postgres is up and ready, Cassandra's up and ready, EpicCollect is connected to Twitter, and if it goes down, we get reconnected, all of these things. And we can't convey all of that in one diagram. We have to have multiple diagrams if we're going to try to give you the overall view of that system. And if you want to learn more about all of that, I give a colloquium today at 3:30 up in ECCR 265. All right, and that was basically the high-level lessons of these lectures. The rest of the slides in this lecture go into detail on each of those things and summarize basically what I had just said. Goes into a little bit about what Fred Brooks was talking about in terms of responding to it. And this is great that I probably won't be testing you on some of this stuff towards the end of the lecture. However, right about halfway in this lecture, I think I switch. No, I ended it. That's right. Okay, so that was the end of that lecture. Okay, so going back to our overview of the semester, and I realized I did want to start this before getting into the details of just a broad overview of the semester, so let me do that real quick. Our basic trajectory this semester has been introducing software engineering, talking a little bit about the theory behind it with respect to No Silver Bullet. Let me skip these two lectures real quick and just jump into here. So lectures 4, 5, and 6 then rounded out that introduction to software engineering. In those lectures is where I went into the types of concerns that software engineers deal with, the different processes that we handle, configuration management, build management, testing, requirements, design, implementation, all those kinds of things. I then also talked about software life cycles, which is once we've got a set of people and a set of resources and we know that we've got a particular goal to achieve, software lifecycle comes in and tells us, here's how you should organize the whole project, here's how you should organize your months, weeks, your day, what's step 1, what's step 2, etc. And so basically lectures 1 to 4, 5, and 6, that all was kind of our intro into software engineering, what's it all about. We then have two topics that we've been discussing at a high level for this course. One is an emphasis on concurrency and how do you design concurrent software systems, and the other is on agile life cycles and the agile approach. Now, because concurrency took a while to get through just the basics, we've only had 3 lectures on agile life cycles. This one here, lecture 7 on the intro to agile, and then user stories, and then finally iteration and release planning. But through those 3 lectures, we have enough to actually, if you want to, after your presentation 2 is done, we have enough for you to launch in and use presentation 3 as a chance to step yourself through a 3-week development life cycle to create a prototype using an agile life cycle. Because we talked a little bit about the philosophy in lecture 7. We talked about how to document requirements in lecture 14, and we talked about how to plan out both a release, which is, once we're done, this is going to be release 0.1 or 0.5 or whatever it is of our software, and then, but working up to that release, we have multiple iterations, and we talked about how we plan those iterations and how the user stories help us with respect to planning both the release and the iterations. So on the concurrency side of things, we've had lectures 8 all the way through lecture 13 that have been, one, providing insight into how hard it is to create concurrent software systems, what are some of the problems that we encounter when we design these systems, and then we spent 2 lectures or so, 9 and 10, on the lowest level primitives that you get from threading libraries. So in C++ and in C and in Java, you can go all the way down to the lowest level primitives, which is create a new thread. Here's a method I want you to run in this separate thread, and here's these locks if you need them, and go. And we talked a lot about the problems that arise from working at such a low level of abstraction. Race conditions, memory visibility, deadlock, live lock were the ones that we looked at. And so I showed a bunch of examples about the types of problems that come in and some of the general approaches to trying to solve those problems. So memory visibility and race conditions, those are insidious problems. They can bite you in various ways. The only way to get rid of them is through synchronization. And so you're either using synchronized, as we've seen in Java, or you're using something like a reentrant lock from the Java util concurrent library to say, here's my critical section. Threads have to acquire the lock before they can go execute that critical section. And we saw this in homework 3 in terms of the types of work you had to do to take that program that had all those weird behaviors and get it to something that would behave consistently every time it was run. And we went through some of the classics to show off deadlock with the Dining Philosopher's problem. And we talked about how that the deadlock occurs when all threads are blocked and nothing is actually happening in your program. And that comes from having a circular dependency among threads. Thread A needs what thread B has, thread B has what needs what thread C has, and thread C has what needs what thread A has. And you get this cycle, and suddenly they're all blocked waiting for them to let go of those resources that they need. And we talked about the standard way of breaking those cycles, which is to provide some sort of ordering on the resources so that there's a known order over them. This is resource 0, this is resource 1, that's resource 2, and then require all threads to acquire resources in the same order. So if someone wants thread 0, or if some thread wants resource 0, and some other thread wants resource 0 as well, both of them have to try to acquire it before acquiring anything else. If you have, as we saw in the Dining Philosopher's problem, if we have one acquire resource, one of them needs resource 4 and resource 0, and the other one needs resource 0 and resource 1, you can't have them go to the outer resources and get those first. You need to make sure that they're both going after the same resource in the same order. So they would both go after resource 0 there. If that happens, then one of them gets blocked but doesn't get the resource. The other one gets the resource, and then this circular dependency chain doesn't kick in. It can use it, let go of stuff, and the one that was blocked can eventually get it and move forward. And then live lock is a little bit more insidious. You can actually see that in the homework 3. There's certain scenarios that will get the consumers looping forever. And so they're not actually blocked, but they're not doing anything. And so you have to watch out. In that case, it was because of synchronization around the length of the queue, and they got the wrong number for what the queue was, what its current state was, and then they went into this loop where they would never check the size again, and they would get stuck in an infinite loop. And so live lock represents this case where no one thread is blocked. They're all making progress. They could all be printing out output, but no actual work is being done because they're waiting for some thread to become some resource to become available without being blocked on it. And then what we started to do was to show ways of getting away from that low-level API. And that's going to be a theme throughout the rest of the semester. We're going to be talking about the agent model, the actor model, Grand Central Dispatch, which is an OS 10 technology, Go's channels model. All of these things, they're much higher level concurrency frameworks now, where you never have to say new thread, you don't have to really do any locking, and you can still get maximal use of your cores and lots of concurrency. And so that's going to be the theme, is to slowly go up layers of abstraction. The threads and all that stuff are still there. We're just not encountering them ourselves. Someone else did the work for us, and we're using higher level primitives to get our concurrency work done. So with respect to that, in this Threads and Locks Part 2, that was one where we started to look at higher level concurrency primitives that Java has to offer, and that's in the Java util concurrency package. We learned about atomic integers, and then really the atomic package. So we looked at an example of atomic integer, but of course that package has atomic longs and doubles and strings, and it can operate on a whole bunch of different data types. We looked at executor pools to do thread pools for us automatically, and how with an executor we can create a runnable and hand it off to the executor and say, hey, go run this at a thread, and I don't care I don't care how it's synchronized or when it runs. Eventually I'll ask for a result back, but it can handle that for us. We looked at the condition variables, and I was quite pleased to see many students actually used condition variables to solve homework 3, which is great to see. So they actually took something from that lecture and applied it right away. And I think there was a few other things. We can go back to it in just a minute to make sure I'm not forgetting everything. But then we switched over to a completely different language to set up a look at some of these higher level concurrency primitives. And so we started learning about Clojure. And the key thing that Clojure does, the so-called evil of the problems with Java is that it's very easy to create threads that share a variable that can change. And so the key thing that makes race conditions so hard is that you've got a variable that's mutable and it's shared. And as soon as you've got that set up where 2 or 3 things share something that can change, that's where race conditions can sneak in, because I can be reading a value that's changing out from under me, or I can be reading something and then going off to do something based on the understanding of that read, and then while I'm doing something, someone else has changed the situation for me, and I really shouldn't be doing my operation because the situation changed. So as an example, in homework 3, it was very possible for a producer to say, hey, is the queue full? And get back the answer, no, it's not. And be completely unaware that 8 other producers were asking the same question. Is the queue full? No, it's not. So they all go and add something to the queue. But it turns out the queue had only 1 empty space left. But when they read it, they all read it and said, hey, how many spaces are left in the queue? 1. Okay, I'll go add 1. But then all 9 of them added 1, and suddenly we were over 10. We had, in some cases, as high as 19 elements in the queue. And it was all because the size of the queue was being read in a stale way. So yeah, it was true, but there were other people reading that same value, and now we all added and changed the value at the same time. And in fact, updates to that size could get stomped on. You could have 2 queues. There's nothing that was guaranteeing the insertion of the item into the queue as being atomic, and so it's possible for multiple producers to stick a different product in the same slot and just have the linked list data structure just really be completely out of sync with what it should have been. And so shared mutability is the evil here. You've got these variables that are mutable, and we share them across threads, and we don't synchronize, and we get into these problems. So what a language like Clojure does is it says, well, it's just impossible to share something that's going to change out from underneath you. So we don't even, and actually I should temper this. We ended by talking about they do have some shared variables, but in general, if you set aside atoms and refs and agents for a moment, all of their variables are immutable. Once you've created a value and pointed at it, that value is never going to change. So what's great about that in the thread context is you have 100 threads, you have a data structure, and you share it among them. There's no chance for a race condition because none of them can change that value. And so this is where we start to get into the basic approach, which is to share nothing. And I haven't really said that phrase before, but this is where we go. When we get to the agent model and the actor model and Go's channels and the Grand Central Dispatch, you go into a share nothing model. So you can't have race conditions if you're the only thread modifying a set of mutable variables. Or if you do share something with some other thread, that particular variable is immutable. And so that was the major lessons there. Some of the kind of more fine-grained lessons was looking at these things where we would design an algorithm to be correct and behave the way we want in a single-threaded context. And we showed how in this functional programming world, you could then do drop-in replacements of some of those functions and suddenly get parallelism going on behind the scenes. And in this lecture 13, we showed a whole framework called the reducers framework designed to do exactly that, where if you're comfortable programming algorithms using map, filter, reduce, take, and some of those other kind of functional primitives, their whole reducers library gives you replacements for all of those functions that you can just swap in to get the same semantics. But behind the scenes, when it executes, it analyzes all of the transformations, creates a DAG, directed acyclic graph, of every transformation that needs to be applied to the data, and does all of that in parallel. And I finished Lecture 13 by saying something that was dead on with how or not finished it, didn't finish the lecture with it, but I finished that section on reducers to try and explain how it does all of this. And it came up when I was discussing the parallel version of count primes, and had this thing here going on where I said the parallel version of count primes, when it was counting the number of prime numbers that there are between 1 and 100 million, I noted that in the single-threaded version we had something which took up 6 to 7 gigabytes of memory, but the parallel version was able to stay at much lower memory, about 3.5 gigabytes of memory. And the reason is that we had this conceptually our program looked like this: produce the range that we're going to be operating over, find which numbers in that range are prime, convert trues to ones and falses to 0 so that we can then sum it up. And in the single-threaded version, it turns out that because of the techniques that we were using to always keep our sequence in memory, this creates one sequence in memory of 100 million elements. This creates a second sequence of memory, a second whole 100 million element sequence in memory, and that created yet a third separate sequence in memory. And so we kept having to make a new copy. There was nothing that could be shared between them because we went from different things, integers to booleans, booleans back to integers, and there was no way for it to share any of that data structure, so I kept having to create entirely new data structures. But what was great about the reducers version of this was that here, in produce range didn't change, but find primes changed. It went and started to use the reducers version of maps, of the map call, and convert to numbers changed by also switching to the reducers version of map. And then finally our sum used the reducers version of reduce. And so what happened here was that it figured out, they could figure out by analyzing these transformations that it's going to take that input sequence and it's going to split them into groups of 512 elements each. And then for each of them, it's going to know that for this particular element in that transformation, I need to find out if it's prime, map it to a number, and then once I've done that for all 512 elements in that group, add those numbers up, and then carry that sum forward. And so what you get in this reducers framework is one collection that's created of the 100 elements, subdivided into 512 groups, which are then reused in memory directly. And then all three transformations, or at least the two primary transformations, going from integers to booleans, then booleans to integers again, being done in place. And then finally a reduce that sums up all of the integers and going through a tree structure to get the final result. And as a result, it could be way more efficient. It could do all the operations rather than doing them sequentially, it could be doing them in line as it was processing these things, and it could avoid having to create multiple sequences in memory, and so it was actually able to do it in lower memory. And all we had to do was take code that went from a use of the map routine to a use of the map routine from reducers here and here, and then using our fold rather than the single-threaded reduce to pull it all together. And so that was an attempt to show you how you could very easily get parallelism for very little cost, and you would spend most of your time just reasoning about what does the single-threaded version have to do, and then get parallelism essentially for free. And then we showed a few more parallelism constructs that Clojure has. We talked about futures. And futures are this basically a mechanism that says take this piece of code and run it in a separate thread. And if it's got a response, and actually in Clojure everything has a response, so at some point I'll ask you for the response. And so when you call code in the future like this here, that plus 1, the summing up the integers 1 through 10 happens in a separate thread, and we have a handle to that future in this sum symbol. And if we ever want to know what the value was, we dereference it. We either call the deref function like this, or we use their syntactic shortcut by putting an at in front of it. And the semantics were, again, if we dereference the variable, the future, and the thread hasn't finished running, then the client that did the dereference blocks, and it will block automatically until the other thread is done, and then it will pick up again once it has its value. But if the other thread had finished already, when we call dereference, then we don't block at all. We just get the value, and we move on our happy way. And then we talked about promises, which have the same semantics of I'm going to create a promise, and if hand you a handle to it. If you ever want the value, you deref it. If it's not ready yet, you block. And so you get the same semantics, that same interaction semantics as futures do, but you have a completely different way of getting that value. Rather than having code automatically launched in the background in a separate thread, you instead have already created separate threads that all share the handle to the promise, and one thread's job is going to be to calculate the value and deliver it, and the other thread's job is going to be to wait for the value to be available and then do something with it. And so it becomes a very easy way of passing values back and forth between threads. And so we showed this example here where we did a meaning of life as a symbol that is actually a promise, and we then we used that promise in the context of the future where we have it run, and in order for this print line statement to execute, we need the value of meaning of life. And since the promise hadn't been used yet, hadn't had anything delivered to it yet, that future spun up a new thread and immediately blocked, waiting for the value. And then we delivered in another thread. In this case, the REPL had a separate, the thread that is responding to our input is a separate thread from that future thread. And then we called deliver to pass that variable in. And so these are kind of higher level constructs. The threads are being created for us when we use future, and then the promise allows us to pass back and forth values among those threads if we need it. All right, and then I think that was as far as I got in that lecture, at least on the lecture on Tuesday. So that's kind of what the journey we've been on with respect to concurrency in this class, was identifying why it's important in that intro to concurrency lecture, then showing the wrong way to do it, or basically the hard way to do it with the low-level primitives, and then showing ways in which you can get away from those low-level primitives and get progressively closer to solutions that are way easier to reason about. Even though with the condition variables, you're having to create a thread. Once you've created the threads, you kind of forget about them. You've got your lock, you have your condition variable. Even that represents a step up in abstraction and the ability to reason about what's going on over just plain synchronization on multiple threads. Okay, and then with respect to agile life cycles, that was the other kind of main theme after we got through the introduction for software engineering, was this this discussion of Agile as being a response to the traditional life cycles and the documentation-heavy life cycles. And the response being, we don't want to build software that way anymore. And so can we come up with another way to build software that doesn't depend so heavily on consistent documentation that's consistently updated throughout the development life cycle? And so we talked about the Agile Manifesto, where they talked about the things that they value over. So they talk about this thing here. So individuals' interactions are more important than processes and tools. Working software is valued more than comprehensive documentation. Collaborating with our customer is more important than contract negotiation. And responding to change is way more important than following some predefined plan. And then from this, we started to talk about, what does this mean? If you adopt these values, how does your life cycles change as a result? And so we talked a little bit about some of the principles that come from the Agile Manifesto and the Agile practices. We looked at 5 of them. There's actually 12 that are out there. But the 5 we looked at, deliver early and often to satisfy the customer, welcome changing requirements, face-to-face communication is best, measure progress against working software, simplicity is essential. And all of these things kind of highlight the Agile approach to software development. We want to be in constant communication with our customer. We want to be frequently showing them what's the current status and getting their feedback on what we've done. We use that so that as their needs change over time, that doesn't become a surprise for us late in the project. It's something that we know about as we're going through the project and altering course to manage. We adopt a bunch of practices that try to help us with be open to change. The traditional life cycles would tend to shut down around change and not want to have change requests come in because, if you think about it, they had done a whole bunch of, paper-based work, requirements documents, design documents, and now they're just finally, after many months, setting down to code, and then suddenly you're going to change something on us, and we have to go back and update all our documents and do all that work again. We were ready to code, right? And so they get into this mindset that these change requests are bad because they realize they have to go all the way back, update the requirements document, update the design document. And so Agile says, we have to get away from that. We have to have conversations. We have to be able to be open to changes. We realized that when we started the project, we didn't have a lot of information. As we learn new things, now suddenly we're ready to make a decision about the direction that the software is supposed to go in. And we measure progress by how much actual software has been delivered to the customer. Now, we can deliver something to the customer, and the customer might choose not to use it. They might look at it and do some production, do some feedback, but maybe they're on their side not totally ready to put it into production. We would still say that we've got those features implemented. They've just chosen not to use this particular prototype. But we are getting to the point where if they wanted to use it, they could use it, right? And that's what we measure our progress against. So when we talk about user stories being completed, that means that we've achieved at least that. We've shown it to the user. It's ready for their use. And so then we talked a little bit about various life cycles. Let me just switch back to Keynote so I can go more quickly through it. Open. This will be lecture 7. So in this lecture, we talked a bit about, after we got through this, we showed extreme programming as an example of one of the Agile life cycles that is out there. And we talked about how it was, kind of the things that it did. And extreme programming says that you should be embracing all of these practices: customer, team member, short iteration cycles, user stories, pair programming, test-driven design. They basically say it's an all or nothing thing. And the reason why they say that is that all these practices are built to support each other. So we can welcome changing requirements because we're always writing test cases and we're refactoring to make sure that the system is in a great state. So that if some new change comes in, it's clear where it's supposed to go, or we can extend something that we've already been creating to handle that case. But if we're not doing refactoring and we're not doing test-driven development and a change request comes in, well then, yeah, we're going to be less certain about our code. We're going to be more resistant to change. So all of these things come into play and support one another. And then what we did is we looked at, let me find it again. Oh, shoot. I just closed the window. I need it. In the user stories, what we did is we did a deep dive on what do user stories, what do user stories do for us, and how do we write them? And so in that lecture, what we did is to take a look at the following things. What were some of the concepts and terminology? What were some of the benefits and limitations? What writing style should we use when we write these user stories? And we had kind of examples throughout. So this all pulled from a book that I used last year in this class called User Stories Applied. It's a great book, but what I will test you on are stuff that appear in this lecture. And basically the idea is that capturing software requirements is a communication problem. So we want to, from our customer, we want to come up with a way that says, what was it that the customer wanted in a way that will remember it and that will trigger our memories of the conversations we had with the customer. And doesn't require us to put too much detail down on paper because those details might shift over time. But it's a way to remember that the requirement exists and we want to be able to have conversations about that requirement moving forward. And so what you do is you create user stories to capture those requirements. And the user stories are brief descriptions of functionality that will be valuable to the user or customer. And we want to implement features not because they're cool, but because they provide value to the user in some way. And so basically these user stories become short written descriptions of a feature. And they remind us to have conversations about that feature to flesh out details moving forward. And what we want to be able to do is, rather than taking those conversations and writing them down or writing a summary of them in natural language text, the better thing to do is to actually put the understanding of our conversation into code via test cases. And so, if we're going to be done with this story, the following 10 tests have to pass. And maybe as we have more conversations with our user, we add tests or we take some tests away. But our understanding of the story becomes something we can execute as opposed to something that we're just trying to maintain as we go forward. And that's the key thing here that makes the lack of 200-page requirements documents be mitigated. So there is some utility in having a huge capture of what the customer said about a conversation. About a requirement, but Agile feels better about saying, our own memory about the conversations we've had will help us with understanding what this user story has to do. We have the high-level short description of what that feature is, and then we've been doing the work to take our understanding of what we need to do and transforming it into tests. And then our tests tell us how close we are. So we might be going through a couple of days where the tests are all failing because we're still building up the software that's going to provide this feature. But the tests are our guide and remind us what it is we're actually trying to do with this particular feature. And so we talk a little bit about, at a high level, one of the key things about user stories was that they need to be written from the customer perspective. So we don't talk about them from the developer's perspective. We need to know what they care about, what's valuable to them. And so an example here of a website that helps people search for jobs, you might have stories that say, a user can post a resume to the website. If I'm going to be looking for jobs, they need to know my resume. I need to be able to search for what jobs are out there on this website. As a company, I need to be able to post new job openings. And I need to be able to review applications. And I might be able to, as a user, I might say, well, only companies in which I've done X, Y, and Z, they can have access to my resume. Everyone else needs to do those things with me. So we write them from the customer's perspective and eventually transform them into tasks, as we discussed in Lecture 15, so that it goes from the customer perspective to a developer perspective, and that's when we start to implement during our iterations. We implement on the tasks. We don't write or change to a developer perspective the story itself. So then we talked about different ways in which the stories can go. There can be very high-level stories which are going to be eventually converted into lots of features, and those are known as epic stories. And then eventually the goal of the team is to take those epic stories, as we learn more about them, to decompose them into smaller stories that eventually become closer to things that can be implemented as features. And towards the end of this lecture, we talked about writing styles. How do we write these things? And we came up with this, or we went through an example of a bad way to do requirements capture. And then we eventually talked about this writing style called INVEST. And INVEST has this notion that every user story should be independent, negotiable, valuable, estimatable. So when we look at it, we can say, oh yeah, that's about 3 days worth of work, or 2 days worth of work. Small and testable. And so then we went into a little bit of detail about each of those characteristics. But the important goal here, the important lesson was, You can have user stories as part of your development, and you can be absolutely awful at how you write them. And if you are absolutely awful in how you write them, it undermines their utility and it'll bring an Agile lifecycle down. And so you can sometimes see companies that say, oh yeah, we tried Agile, but we couldn't make it work. And so then you ask them, well, why? What happened? And you find out that they just weren't able, either through company culture or through management or through their own willingness, they just didn't go all the way. They just sampled a few things about Agile, but didn't bring it in. So if you're not doing all the Agile practices, the ones that you do perform don't get supported in the way they would if you were doing all of them, and so that they can fail. You also, if you're used to writing 200-page requirements documents, and now they tell you to write index cards for those requirements, you're going to be reluctant to just write a sentence and call it a day. And so you might have an index card that's just filled with lots of little text, both front and back, which is just their 200-page document being stuck on an index card. And then once you do that, the utility of those index cards, those user stories, just goes away. And so there's lots of bad ways of doing it that then undermine the ability and give a bad reputation to the Agile approach. So we went into some details about this particular writing style, and we discussed different ways in which user stories could be captured. Trello is often used for this, so that you can put up little cards. If you've ever used Trello, you know that you can go up to one of these cards and click on it, and it flips around and has more detail, like who's assigned and a little bit of background information. When you flip the card back over, it's just this short statement that says, here's what needs to get done. And in Trello, this is more oriented towards the day-to-day work of an iteration, and so these are more likely to be tasks. But you can create a Trello board that you only look at during iteration planning or release planning, and that would be where your user stories are, and you just treat those different than you do your tasks. But oftentimes, Trello boards have these vertical separations, vertical columns, so each one of these things here is a separate story or task, and the horizontal columns are used to track status. So this is to do, no one's working on this yet. These three are being actively worked on, and these are all being done. And so you can organize this. Now the Agile life cycles will all say it's good to have this up on the whiteboard somewhere so that you can physically have to, I'm done with this task, and move it, and your small team of people can see the progress. But there are, of course, all sorts of software-based solutions to this. Trello is one. Rally Software has another. You can find it in plenty of other tools. All right, and so that's what we did as our arc for our Agile life cycles, was this intro, why do we need the Agile life cycles, and what are some of the differences between it and more traditional life cycles. And then we looked in depth at user stories, which are the key input into Agile life cycles. And once you have those user stories, we talked about how you use them to plan out releases and iterations. Okay, so that's the end of my kind of overview. And what I'd like to do for these last 15 minutes is take questions from the students here. If there's anything here that you'd like me to go into detail or clarification questions about the midterm, I'm happy to do that now.
I have a question on quiz 1. Question 15 says that a client thinks that it's not a problem to ask a team to create a client-server version of an application 2 months after asking for a standalone desktop application. Why is this changeability and not conformity?
Why is this changeability and not conformity? Okay, yes. So the reason for that being more changeability than conformity is that it relates back to the discussion around the definition of changeability. So in that discussion of changeability, we had the various themes there. One is users don't understand when they're making a simple request versus a hard request, and they'll treat those different types of requests as equivalent, and developers have to then go back and say, no, changing the layout is something that's simple, changing the architecture of the system is hard. This I can do in a day, this will take me 6 months. And the pressure to change and to treat all changes equivalently is related to that definition of changeability. And so that's the reason why that particular question, I put it under changeability. Now you could say with conformity, it is true that their change request could be interpreted as arbitrary, like they heard about this phrase and now they want their system to have that buzzword, for instance, and so they don't understand it, but they ask, can my system be that way? That would be an aspect of conformity. But in that particular sentence, we captured more issues that were related to the changeability equation, and that's why I went that way. There may be, if there had been something in that sentence about how we've always used systems this way, our company understands it, so even though you want to do this other approach, we really want to have the desktop approach or whatever it is that they do, then there where they're referring to more legacy concerns, legacy environment concerns is the reason why they're making the change request, then that could edge in over to conformity. We're being asked to conform to some existing environment. But yeah, actually that's something I never did in that Fred Brooks example. I didn't have time, but I had in that lecture a slide where I wanted you to test yourself on identifying, is this a statement about an essential difficulty or an accidental difficulty? So, a bug in a financial system is discovered that came from a conflict in state and federal regulations on a particular type of transaction. So is that an accidental difficulty or is that an essential difficulty? What do you think?
Essential.
That's essential. That's correct. And that would be what type of essential difficulty?
Conformity.
Conformity, exactly. Yeah, so here we have an external group, the government in this case, or two governments, the state government and the federal government, creating regulations that somehow imposed its way onto us. And our bug was the fact that there was a conflict. We implemented the state regulations, and that turned out to be incorrect with respect to the federal regulations, or vice versa. That would be definitely an essential difficulty. Okay, a program developed in 2 weeks using a whiz-bang new application framework is unable to handle multiple threads since the framework is not thread-safe.
Accident.
Accidental. It's all related to the particular tool that we decided to use. A new version of a compiler generates code that crashes on 32-bit architectures. The previous version did not. Accidental. And then a fickle customer submits 10 change requests per week after receiving the first usable version of a software system. And that's essential. Yeah, they're just like, suddenly they're really excited, and so they're just spamming us with change requests, and we're just like, oh wait, whoa, whoa, whoa! For this iteration, we have these stories. We agreed on these stories, right? That kind of thing.
And this is changeability.
And this would be again changeability. Yes, exactly. So these are the sorts of things I might put up on the test, statements like this, and we're trying to hearken back to some of the discussions around the definitions. Other questions?
Yes. Quiz question 13, same idea. Your software lifecycle requires a code review at the end of each iteration, and these reviews take so long that it pushes your schedule back by 2 days each time. This is an example of accidental, just because code reviews are a tool.
They're a technique. Yeah, it's a technique. That's right. And so we chose this particular code review process, and every time we do it, it just takes forever, and it's pushing back our iterations.
So tools aren't just physical pieces of software.
No, and that's why I try to say tools and techniques. Yeah, processes. We chose this process, and now we get its warts and we get its benefits.
But could you not argue in that case saying that since software has an essential difficulty, which is invisibility, it's very hard to express software in terms of like physical?
It is, but in this case, it was very clear that the choice of technique was causing problems to us. And yeah, it might be the fact that the code review is taking so long because it's hard to deal with that. But in this particular case, the way that one was written, it was really emphasizing this technique was pushing us back. And that's more of an accidental difficulty.
Your software lifecycle requires.
Yeah, But yeah, no, and that's true. I mean, if it's code reviews are taking a long time, there's probably some complexity you're working through. So what's the primary thing that is being referenced there? And that kind of background, yes, things are always going to be complex, wasn't as prominent in what the sentence was saying, and so I was looking for the accidental in that case. Yes?
Do we need to learn about the code behind the producer-consumer example at the end of lecture 10, I guess?
Lecture 10. Oh, yes. So, yeah. Let me see here. Open lecture 10. Yes, so that was the last example, which is that word count example on the very big Wikipedia XML file. So yes and no. So, I'm not going to go in and ask you questions on its parsing code, for instance. Completely not important. But what was important in this example was the progression of, here's the single-threaded version of this program. What was the first attempt we took at making it parallel? And then it turned out that that wasn't all that parallel. So then what was the second attempt to make it parallel? And that failed. And then what was the third attempt that was ultimately, gave us the most parallelization? And so the concepts behind the problems that were being called are ones that I would like you to be aware of. So the first attempt was to try to make it a producer-consumer system, going from a single-threaded version to one that had the producer and the consumer running in separate threads, and seeing, if I just do that, is it faster? And it turned out not to be all that much faster. Then what we said was, well, let's have more consumers. So we'll add more consumers, and they all have to count and put it in a shared data structure. And because it's a shared data structure, we have to lock it. Because it's locked, we have high contention, right? And so as a result, that particular version was actually slower than the single-threaded version, because our consumers, and also we were doing a really silly thing in which we were reading a word and immediately adding it to the count, getting the next word and immediately adding it to the count. And so that's all we're doing is getting words and putting it in, and so there was huge contention around that, which slowed us down. And then the final solution was like, yeah, it's stupid to be counting every word and having to get that lock again. What I should have is my own copy of a map table, and I can just count as fast as I can on all the words coming to me in my own local copy. And then once I'm told I have no more pages, then I turn and merge it into the final hash table. And so what that did was it allowed the consumers to not have to, it took high contention and reduced it to low contention. It also, there might be high contention in that particular application, but it's only at the very end. And so we can run as fast as possible all the way to the very end, and then the consumers might be fighting to merge their results in. But rather than fighting every step of the way, that fight only happens at the end when most of the work is already done. And so we had to figure out a way in which we could take multiple threads and understand that they were fighting each other and come and migrate to a solution that would allow them to be able to run in parallel without having to depend on each other. And so that's the lesson that's important there. Because I might, as one example, put some code up and then say the following problem occurs. How would we change this code? You don't have to write the code, but what's the strategy? What would be the next thing you'd want to do to try to make this faster? And so these techniques that the book steps through and going from single-threaded to as parallel as we can get is the types of strategies that would be useful in answering those types of questions. Details about the specific source code of this example, not so much. But the understanding of the design and how it evolved, definitely. It's a good question. And then back here, I didn't go into details today, but just as a reference, in these software engineering, these two lectures on the life cycles and on the intro to software engineering, in the intro to software engineering, that's the one where I talked about testing. And so we had the concepts of fault and failure and error. And, not all, we had that whole sentence about, I better make sure I say it correctly. Where was it here? Go past all that to the faults. Yeah, so you have the error is the mistake made by an engineer in misunderstanding a requirement or design. The fault is the manifestation of that error in the code, what we typically call a bug. The failure is then an incorrect output or behavior that is caused by executing a fault. And so a couple of these things here. Testing then, seen it at a high level, our goal is to surface failures, make failures appear. Because as soon as we see a failure, we know there's a bug. And so then, as soon as we see a failure, we can do debugging. And debugging is that high-level process that says, we have a failure, go find the fault. We know it's there. So the problem, of course, comes in the fact that we have done all these test cases. We're running them, and every time we get back, tests pass. And so we have this question here, if a system passes all of its tests, is it free of faults? And the depressing assertion is that we can never make that statement. And maybe we can on very small systems where we can either manually or automatedly go through every path through the system. Maybe then you could. But on very large systems, millions of lines of code, you can never assert with any confidence that you're free of faults. All you can say is, on our current set of tests, no failures manifest. But the reason for that, if you remember, was I have seen situations in which faults mask each other. Two bugs prevent a failure from occurring. And that one, that was that example where I said, you know, it makes you question your sanity because you're going along in the code doing something else, and then you see something that's clearly wrong. And you go, how can the system be working? This is completely wrong. So you fix it, and then it crashes, right? Because then the other bug kicks in. And then, so that's one aspect. The other aspect is the system can be so huge in terms of paths through it that our test cases, you know, we talked about our coverage criteria. Our test cases could be doing 80% of the paths, and there's 20% of the paths that are just never being executed. And then you have a bug that's sitting in one of those paths. And so then you deploy, and one of your users figures out how we can get down the branch that we'd ever tested, and then the bug appears. So there are ways for faults to hide in a system and not manifest, even though all of our tests are saying they pass. So don't forget about this. This will be something that's, for one thing, it's very easy to test. I can write, you know, define the three terms, error, fault, failure. I can ask you, if you see this, all your test cases are passed, why is it that we can't say it's fault-free? You know, all those kinds of things are very easy to test, and so will appear on the midterm. We talked a little bit about, you know, what you're supposed to be doing with test cases, this notion of if this oval represents all the possible behaviors of your system, a test case can be seen as a point in space and saying, is our system behaving correctly if we direct it to this point in space? And then we, of course, you know, we say that, you know, conceptually a system will have millions and, you know, an infinite number of these points. And so the way forward is to say, yes, it's true, there's an infinite number of states that the system could be in, but they broadly cluster in these ways. These are the functional behaviors we expect. And so this is called folding the space. And so then testing becomes this notion of what are the different conceptual behaviors our system can do, and how much sampling can we do of that behavior. So yes, there's an infinite number, but if we know there's 5 different things, if we've tested it, for each one of those 5 different behaviors, we've tested, you know, 10 different instances, maybe that's good enough. And so actually testing is all about what's good enough. When do we decide as a company that this system has been tested well enough, right? And on the black box testing side, the way you decide that you're done is to say things like, well, what are the high-level functional requirements of this system, and do we have test cases for all of those functional requirements? But you can also do white box testing, which we talked about down here somewhere. Down here, black box, gray box, white box. White box testing says, well, let's just test the code independent of the functions, and do things like have all statements be covered, have all branches covered, have all loops, you know, executed at least a couple of times, and at some point decide that's good enough. And so what testing does is help us be concrete in saying this is acceptable for our organization. So there'll be organizations out there dealing with billions of lines of code. They might say, if we have 75% branch coverage, good enough, we can ship that, right? And so as your scale increases, your thresholds will change as to what you expect to be able to test in your system. So don't forget about this. This is an important part of what we covered. All right, so we have 2 minutes left. Anyone have one last question?
How long will the midterm take?
The midterm is designed to be one lecture section. So we have an hour and 15 minutes. We do have a class right after us, and so what I'll typically do is go 1 hour and 20 minutes. So rather than ending right at, what do we do, 12:30 to 1:45 normally, rather than ending right at 1:45, I let people go 5 more minutes, and then at 1:50, then I'll demand all the tests, because then we have to clear out because the next class is rolling in. So it's an hour, 20 minutes. It'll be closed book, closed notes. But the style of questions will be like what you've seen on quizzes and homeworks. Short answer, typically, or writing a little bit of code to recommend, to identify or fix a problem that is in some sample code that I give you.
We're going to be testing on Git?
I probably will test on Git, yes. I didn't talk about it today, but I had those 2 lectures on Git and Markdown, and we had some homeworks on it, so yes, I'll probably have a couple of questions on that.
And reading?
On the reading?
Yeah.
Oh, yes. So on the reading, yes, I would like you to make, the only textbook we've gotten to so far is the concurrency textbook, chapters 1, 2, 3, and a little bit of 4 by the end of lecture today.
Should we go back and make sure that we've read all of that, or is it good enough to have,
It's good. It's at the level of the strategies, as I was discussing before. So some of that more tactical information that he covers is what I'm looking for, as opposed to memorization of syntax or APIs.
Okay, so there's stuff in the reading that's not covered in the lecture that we want to make sure that
Make sure you have, because it supplements what I cover.
What could be some questions on Clojure?
On Clojure, I could ask. I might give you a program that uses the reducers framework, for instance, and then ask questions about that, like what's the value of this function? What is the overall behavior that we might see out of this? Those kinds of things. We're going to be covering, I believe I can't remember, is it agents or atoms today in the next lecture? Let me just make sure I understand that keynote so I don't say it wrong. We are going to be covering at the very end of this lecture, we didn't get to it last time, atoms. So atoms have a particular API. I can create them. I can swap values. So I might have a question about atoms, which says, it starts out with this value, and I change it this. What does this thread do? Those kinds of things. All right. Well, thanks very much for being here. I appreciate having the audience. The next, as a logistical thing, next week, these lectures will play in the classroom during our appointed time, but they'll also be available on D2L. And this weekend, I'll roll out a quiz that will help you study for the midterm. All right. Thank you.
How have you guys been accessing the quiz?
Yeah, you should be able to go back to your submission.